Now the next thing we can see with the light from stars is its spectrum, and it depicts the energy it emits at each wavelength. The spectrum can also reveal a star's composition, its temperature, its luminosity, its velocity or speed in space, how fast it's rotating, and other properties. And on certain occasions it can even reveal the mass of a star and its radius. So being able to figure out the spectra of a star is a very important measurement. So as light moves through the gas of a star's surface layer, the atoms there absorb radiation at some wavelengths, and that creates a dark absorption line in the sun's and the star's spectra. Every atom, we've learned, creates its own unique set of absorption lines. So determining a star's surface composition is then just a matter of matching a star's absorption lines to those known for atoms. So to find the quantity of a given atom in a star, we use the darkness of the absorption line. The darker or wider the absorption line, the more material there is. This technique of determining composition and abundance can be tricky. There is possible overlap of absorption lines from several varieties of atoms being present, and temperature can also affect how strong or how dark an absorption line is. So how does temperature affect it? A photon is absorbed when its energy matches the difference between two electron energy levels and an electron occupies the lower energy level. At high temperature, there's lots of collisions and energy exchange, and sometimes force the electrons on average to occupy higher energy levels. Lower temperatures are lower electron levels. So at higher temperatures, sometimes light's not absorbed at a certain place because there's no electrons in that place. Consequently, absorption lines will be present or absent depending on the presence or absence of an electron at the right energy level, and this is very much dependent on temperature. So, if we do that and we adjust for temperature, a star's composition can be found. And interestingly, virtually all stars we see in the sky have very similar composition to the Sun, about 71% hydrogen, 27% helium, and about 2% the mix of the remaining elements. This is an important piece of information when we're trying to look at the structure of the universe as a whole. Now historically, stars were classified into 4 groups according to their color: white, yellow, red, and deep red. And those were subsequently divided into classes using the letters A through N. Now Annie Jump Cannon discovered the classes were more orderly in appearance if we rearranged those by temperature, not by color. Her reordered sequence became O, B, A, F, G, K, M. O and B being the hottest stars and M the coolest. And today these are known as spectral classes. Cecilia Payne then demonstrated there was a physical connection between temperature and the resulting absorption lines. So if we look at the spectra for different stars, this is an O-type star, B, A, down to an M-type star, you see that the spectra are different. The cooler stars have more transition levels in the visible, so you get more dark lines. Whereas an A line, an A spectra, there's some lines that really aren't visible that become very strong in an A-type star and start to weaken again. So which absorption lines I get depend on the temperature of the star. Now O, B, A, F, G, and everything are also going to be subdivided into different classes. So and an O star is going to be 35,000 degrees Kelvin at its temperature. We said the Sun is right around here. It's a G-type star. And notice here, this is kind of a finer graded absorption spectra, and you can see how some spectra here fade out depending on temperature. Some grow and then fade out at higher temperatures, and so then by looking at the spectra I have a better way of measuring temperature than Wayne's law. O stars are very hot, and the weak hydrogen absorption line indicates that hydrogen is very ionized in the hot stars. A stars have just the right temperature to put electrons into hydrogen's second energy level, which results in strong absorption lines in the visible light. F, G, and K stars are low enough in temperature to show absorption lines of metals like calcium and iron, elements that are ionized in hotter stars. And K and M stars are cool enough to form molecules, and the absorption bands become evident. A molecule might absorb over a band or a wide area of wavelengths as opposed to just a very specific one. The temperature, the surface temperature, ranges from more than 25,000 for K and O stars to less than 3,500 degrees Kelvin for M stars. Again, spectral classes can be subdivided by numbers. The Sun is a G2 star. Now I said we could also measure a star's motion from spectra. We can determine that from the Doppler shift of its spectral lines. The moving of certain spectral lines, we know where they are, either one to the red side or the blue side. The amount of shift depends on the star's radial velocity. That's the star's speed along our line of sight, how far it's moving towards us or away from us. Given that we measure a shift delta lambda, delta just means change in mathematics, and lambda is our wavelength, so the change in wavelength over what we know the wavelength should be times the speed of light gives us the velocity. We can measure the star's velocity coming towards us or away from us with very good accuracy. So lambda is the wavelength of the absorption line of an object at rest, and its value is determined from laboratory measurements on non-moving sources. An increase in wavelength means the star is moving away. I get a red shift. A decrease or a blue shift means it's moving towards us. Now, any speed across our line of sight can't be determined, only speed coming towards or away from us. Doppler measurements and analysis show that all stars are moving and that those near the Sun share approximately the same direction and speed of revolution, about 200 kilometers per second, around the center of our galaxy. Superimposed on this orbital motion are small random motions of about 20 kilometers per second. In addition to their motion through space, stars spin on their axes, and the spin can be measured using Doppler shift techniques. Young stars are found to rotate faster than older stars.